All right, we're back. We're on page 2 of note 17 from Calc AB. We're talking about something called the second fundamental theorem, but so far all we've really done is look at what are called accumulation functions. Accumulation functions are functions that have definite integrals in them, and that is weird until you get used to it, and then they are awesome. So in the last problem, we spent a lot of time trying to figure out, like, how do we get rid of the integral sign? We use the fundamental theorem, and then we would sub in, and basically we would create a non-accumulation function out of our accumulation function. That, generally speaking, does not actually work. So the reason I was doing that was to illustrate something that we're going to do in a second, but usually your accumulation function is weirder, right? So like maybe your accumulation function looks like that. Do you know a function whose derivative is e to the t squared? I guarantee you that you do not, because this doesn't have a simple antiderivative. So we can't look at that and just be like, oh, e to the t squared, that's the derivative of what? It doesn't have one. So this accumulation function will always need to have that integral sign, which means that we can figure out values of the function. We can find f of 1, right? It's just the integral from 0 to 1. Let your calculator do the work. You find f of -1, integral from 0 to -1, which you should flip and make the integral from the negative of the integral from -1 to 0. But still, it's just the calculator is just going to do the work. We can find any value. We can graph that function because we can find as many points on the function as we need. But how do we deal with, like, what's its rate of change? What's its concavity? That's what we need to learn. So let's see what we can do. So these, I copied them over because I didn't want to make you watch that. These are the problems that we did on the previous page. So we did the integral from 1 to sine of x of 3 dt, and we got 3 sine of x minus 3, and so on. What we're going to do now is we're just going to find the derivatives of these things. So f prime of x is, I'm going to find the derivative, basically, of this. Well, not basically, actually, of that. What is the derivative of that? Okay, so I'm going to say that it is 3 times the derivative of sine is cosine of x. And then the -3 just disappears. Okay, I'm just going to leave that. There's nothing exciting about that, right? The derivative of sine is cosine, so 3 times cosine. Not a big deal. Let's find the derivative of this one. So here, f prime of x. All right, the derivative of sine of 2x is going to be 2 times the cosine of 2x. And then the derivative of 2x is 2, so plus 2. I'm going to rewrite this. Why would I do that? Well, I'm going to do that because I know what we're doing. So I'm going to rewrite it like this, plus 2. Oh, no, plus 1. And then times 2. Okay, doing it for reasons. We'll see in a minute. Let's find the derivative of this. So f prime of t. Well, this one's annoying because we're going to have to use the product rule and blah, blah, blah. So first, the derivative of the second is 1 over t. It's actually 2t over, so it's 2 over t. It's really 2t divided by t squared, which is 2 over t. Right, it's 1 over u times the derivative of u. And then plus the second, which is a natural log of t squared, times the derivative of the first, which is 2t. And then minus 2t. Okay, so what does this do? So this is, so here it's 2t plus the natural log of t squared times 2t minus 2t. So actually we just get the natural log of t squared times 2t. So that's what f prime of t has ended up. So I'm seeing a little bit of a thing here. And that little bit of a thing here looks kind of like, so bear with me here, right? So in this one, I see this 3 and I see that 3. And then the derivative of sine is cosine. So it's like I had the integrand and then times the derivative of the upper bound. Let's see how consistently that works. So here, the integrand is cosine of t plus 1. And when I simplified it, I ended up with the cosine and the plus 1, but I had the upper bound subbed in. The upper bound here is 2x. Then I had the derivative of 2x. Let's look at this one. So here I have the integrand, but I have the upper bound subbed in. And then, so here's the upper bound, I also have times the derivative of the upper bound. So with that in mind, it seems like maybe f prime of x here will be, it seems like it'll be this integrand with the upper bound subbed in. So I'm thinking that I'm going to get the quantity 2x squared plus 1, right? So every t became an x squared, times 2x, which is the derivative of the upper bound. So this from here, and then this was like 2 and plus 1, and then this was the upper bound that we subbed in. So it looks like maybe that works. Let's actually find the derivative and see if it does look like that. So f prime of x is going to be 4x cubed plus 2x, which is, we can take out 2x, and we'll be left with 2x squared plus 1. And it worked. Okay, so it looks like maybe there's a pattern here. And there actually is a pattern. And that pattern is called the second fundamental theorem of calculus. It tells you how to find the derivative of an accumulation function. And honestly, of the two fundamental theorems, this one is way easier to use because you don't have to find an antiderivative. There's very little to be done here, right? Derivatives are easier to find than antiderivatives. I think everyone can agree with that. As long as you remember the chain rule here, you will get these right. So what this says is that if we want to find the derivative of the integral from a to g of x, so g of x is our upper bound. So notice the upper bound is the function. If you had g of x to a, we would flip it and change the sign and make it negative of the integral from a to g. So the upper bound has to be the function. If you have that, then what you're going to do is you're going to do the integrand evaluated at the upper bound times the derivative of the upper bound, which is literally just the chain rule. That's all you're using. And so let's see why this is true. So we just did it several times, right? So if I wanted this, so I know we just did it, but let me just show you, or I think I crashed this. Get back. Okay, so if I wanted to find this derivative, I would say that f prime of x is, so the integrand is 3. 3 evaluated at everything is 3. So it's going to be 3 times the derivative of the upper bound, which is cosine of x. Done. Here, if I wanted to find the derivative using the second fundamental theorem, f prime of x, it's going to be cosine of t plus 1 with the upper bound subbed in. So if you sub in the upper bound, you're going to get cosine of t becomes 2x, plus 1 has no t's in it, so it doesn't matter, times the derivative of the upper bound. You're done. You never needed that antiderivative. You did not need to find it. Here, okay, f prime of x, it's going to be natural log with, oh, f prime of t, I should say. I was like, in my mind, I was like, it's spelled wrong. What's going on? Okay, the integrand natural log of x with t squared plugged in, so natural log of t squared times the derivative of t squared times 2t. And it worked. And then here, it's just going to keep working. So that's the second fundamental theorem. So much easier to use. The weird thing is the value of a, that lower bound that's a constant, it doesn't matter what that value is. It could literally be anything in the domain. And this is going to work. And you'll see now why. So let's see if we can figure out how it works. So to do this, you need to use my least favorite convention in all of calculus. Let capital F of x be an antiderivative of lowercase f of x. How are you supposed to say that? Big F and little f? Like, I don't really know. So if that's the case, then here I can say, so the antiderivative of little f is big F, and then we're going to use a fundamental theorem. So you go from a to g of x. So this gives me capital F of g of x minus capital F of a. So the weird thing, it's not weird. The thing here that's a constant. And so since this is a constant, and the derivative of a constant is 0, when I take the derivative to find h prime, it's going away. It doesn't matter what it is. A could be any number, and the derivative of that constant will go away. So the lower bound doesn't really matter as long as the lower bound is a number, which is a big deal. It needs to be a number, but if it is a number, it's just going away, so it doesn't matter. So if I find the derivative with respect to x of f of g of x minus f of a, I'm going to get the derivative of f of x is of capital F is little f. So I'm going to get little f of g of x. So this is a chain rule problem times g prime of x, and then minus 0. That's where it comes from. So this right here, that's not a good color to use. This is what we're trying to find, right? We're finding the derivative of this. If I find the derivative of this, it's going to be the integrand, which is lowercase f, evaluated at the upper bound, so lowercase f of g of x, times the derivative of the upper bound, g prime of x. Where does that derivative of the upper bound come from? The chain rule. We just did it. So really, I think anybody can get good at this. This is a very straightforward rule for it to be one of the fundamental rules. Or I don't know, maybe you think fundamental rules should be simple. I tend to think fundamental rules should be like a very low level, deep, kind of maybe complicated thing. I don't know why I feel that way. Like I don't feel like it should be built on this simple foundation. I feel like it should be built on a complicated, a lot of gears and a lot of things going on. Second fundamental theorem though, really straightforward. So this is your second fundamental theorem, and you need to remember it always and use it correctly. So upper bound needs to be a function. Lower bound doesn't matter as long as it's a number, and it's going to be integrand evaluated at the upper bound times the derivative of the upper bound by the chain rule. The chain rule is what's making that happen. All right, so I'm going to actually end this here, and I will come back in the next video and do more stuff with this, and we'll see how it goes. So I will see you there.